lecture 4.3, types of engines, that is combustion and diesel, and examples. We will look at two different types of heat engines. It's really the working fluid. That's really the big difference here. We're going to look at the Otto gasoline cycle versus the diesel cycle. There are other important examples. There's the Batron that we looked at, but that's more educational. When we were looking at the nuclear power plant in example 4.1. There's also the Stirling engine, and we could go on, but these are the two that are probably the most important. So let's start off with the first one. So this is the Otto gasoline engine. As far as heat engines, this has to be the most familiar. That's what we see on a daily basis here. So when I'm looking at this, we could then say that I'm going to give you the basics of the gasoline engine first. The gasoline engine used in automobiles has this basic structure. So I made this image big so that we can clearly see it. Okay, so when I look at this thing, let's start listing some of the things here. Right here, which I'll call one, this here is the crankshaft. Now, there's a crankshaft rod, but I don't really care about that. Then the second thing here is this is two here. Two here is the piston head. And you could see that the crankshaft moves the piston head up and down as it moves in a circle here. Then we have three, and this three right here is the combustion chamber. And then what you're seeing right here is that what's coming in right here, as you can see, that this is, I'll call this 4. 4 is it's air fuel mixture. And then what you're going to find here is where that air is actually coming in, which is what I'll call 5. This is what's called the intake valve. And then right here at 6 right here, 6 here is the spark plug. And then finally, there's this guy right here, and this is 7, and this is the exhaust valve. So I have a video that I'm going to show you right now, but let's essentially look at just the overall process before we look at the video, so you have a better sense of what you're looking at. So the cycle looks something like this. The intake valve opens up, and as it opens up, it allows the air-fuel mixture to go into the combustion chamber. Then what happens next is you could see here that the valve on the left is now all the way up, which means that it's closed. So right here, now you see that I have a closed valve. And so now at the same time, the piston head is now moving upwards. Now this happens so fast that it's essentially an adiabatic compression. Adiabatic compression says that the temperature increases not due to heating, but the work done by the piston head compressing the gas. And then with both valves closed, now the spark plug ignites a flame or a spark, and it ignites the air-gas mixture. And so now you have a little bit of an explosion, and that explosion now forces the piston head to go back down. So now I have spent fluid, and what you're seeing here is that this exhaust valve, now you have an open exhaust valve, and then it pushes the air out. So now what I want to do here is that I want to go look at a video here. And so this is a gasoline engine video. And I don't remember what the number it is, but here, let me go share my screen so you could see what I'm looking at. Here I go. So this is for a company. I fast forwarded to 1:15, and I'm going to run it till 4 minutes, and it explains it pretty well with images. Here you go.
A four-stroke engine, it represents an example of efficiency and perfect synchronization. It converts the explosions that occur inside its combustion chambers into motion. The aim of this engine is to use this energy to provide movement and transfer it to the wheels so that the vehicle can move. It all takes place inside the cylinder. Here, we can find the combustion chamber where the explosions occur. The cylinder is basically the space through which the piston travels. The purpose of the piston is to transfer force from expanding gas in the cylinder to the crankshaft via a piston rod or a connecting rod, so that the back and forth linear motion of the pistons is transformed into a circular motion which can power the wheels. But let's see this process more in detail by disassembling the engine. The term four-stroke is referring to the cycle of engine operation, which requires 4 strokes of the piston. First stroke, intake. The valve must be in the open position while the piston pulls an air-fuel mixture into the cylinder by producing vacuum pressure through its downward motion. The air-fuel ratio is generally about 14.7 to 1. That's because fuel cannot ignite alone. It is the oxygen in the air, in fact, that provides the combustion of the fuel. What happens now that the air-fuel mixture is inside the cylinder? Second stroke, compression. During this stage, both the intake and exhaust valves are closed, and the piston moves up the chamber to the top. This causes the compression of the fuel-air mixture, which decreases 10 times its volume. At this point, pressure rises drastically as the air and fuel molecules are compressed together, colliding with each other and increasing the temperature. Now we are ready for the explosion. Third stroke, combustion and expansion. At the top of the compression stroke, the spark plug fires, igniting the compressed air-fuel mixture. This causes an explosion. As the fuel burns, it expands, increasing the pressure inside the cylinder and driving the piston downward, moving the twist that rotates the crankshaft, which will convert the energy of the explosion into rotary motion. Now, let's see the fourth and final stroke, which is called exhaust. During the exhaust stroke, the piston once again returns to the top while the exhaust valve is open. This action expels the spent air-fuel mixture through the exhaust valve. The 4-stroke cycle is complete, but it does not stop here.
Okay, I want to stop it right there, but you see the whole process right there. So what I want to do now is that I want to go back to my screen and show you what I'm thinking about here. So let's go back through what we were just talking about. So if I look at the cycle, so this is the PV diagram of an auto gasoline engine. And this is assuming a idealized engine. So what I'm going to do here is that as I draw this out, you're going to see that there's a minimum volume, and then there's a maximum volume. And this maximum volume is typically written as R times V initial here, where R is defined, what do they call it again? They call it the compression ratio. And I think most American cars have a ratio of 10. So I'm going to just assume that. It could be lower, but that's what that is here. So then what we're going to see here is that this is the point where I have atmospheric pressure because it's open there. And then up here, I'm going to get that this here is P maximum pressure. That's what the compression. So here we go. So what we do here is we start off at the maximum volume. And what you're doing in here is that you open the valve and you are essentially allowing the air to come in. So now when you have this volume of air, now what happens here is that the pressure now increases to some point, let's call it right here, 2. So if I'm looking at my cycle then is coming in here like this. And what you're seeing here is that this is a process here, this process right here, this is an adiabatic compression. So what we know here, so if I go from 1 to 2, then what you're seeing here is that this is an adiabatic compression. And according to an adiabatic compression here, we know then that Q12 plus but work 12 has to equal the change in internal energy. But if it's approximately adiabatic, then that means that the heat here is 0. So what you're finding in this situation, that since this is positive, right? This is a positive change in internal energy because you're doing positive thermal work. You get a dramatic increase in temperature. But not through heating. Not through heating. This is the work done by the piston that increases microkinetic energy and therefore changes the internal energy. Now what happens is that there is a process of isobaric heating. So now what happens, you then go through I said isobaric, I meant isochoric heating. This is going to get in the way, so I'm going to move this right over here. So I go through isochoric heating, which then means that the heat from 2 to 3 plus the work from 2 to 3 must equal the change in internal energy between 2 and 3. But because this is isochoric, we know that that's 0 here. So in this case, what's going to happen here is that when I do this heating here, now there's an increase in pressure at this point. Now here's where it becomes really important what actually happens. So what this means here, here's where the heat is coming in. So then Q hot is equal to Q23. So that's where that comes in. And what you're seeing here is that at this spot right here, right in here, what you're going to get here is you're going to get the ignition by spark plug. So this is, the ignition is just right before it gets to maximum pressure. So now I know what my heating is here, okay? This guy now becomes important because I know that to calculate the efficiency, I'm going to need that Q hot. So now what happens next here? I'm going to have an adiabatic expansion. And this is what they call the power stroke. So the power stroke, by the way, I should have been putting numbers. So this is 1, 2, 3. So when I look at the power stroke, this right here is now, this is an adiabatic expansion. So when I look at this adiabatic, as I go from 3 to 1, nope, not 3 to 1, 3 to 4, we're seeing here that you're what you're getting here is that this is going to be an adiabatic expansion that does work in pushing down the piston. So that means here then that the heat from 3 to 4 plus the work of 3 to 4 must equal the change in internal energy. Since there's no heating at this point, then that means if it's an expansion, then that means that has to be negative. Okay, it has to be negative. And again, this is what they call the power stroke. So you're expanding all the way to the maximum volume. And then finally, we then do isochoric cooling. So what you're seeing here is that there's got to be a decrease in internal energy. So then as I go from 4 to 1, I now have isochoric cooling, which then means, of course, that heating has to leave the system as I go from 4 to 1. Which is now negative. Of course, because it's isochoric, this is 0. So then if I go and I start to calculate the details of the efficiencies here, then this is what I need right here. So then calculating the efficiency, there's 2 ways to do it. One, the efficiency of the engine can be written as the work out divided by Q hot. So if I look at the details, what does this mean here? Well, I need the area of that curve. So if I look at the area of this curve, what we're really looking at here is that we're going to look at the work from 3 to 4 minus the work from 2 to 1. And that quantity has to be a positive quantity. So it's the difference between these two divided by the hot heat, which in this case is going to be 2 to 3. That's one way to calculate the efficiency here. So this way would be now the engine efficiency. Now, if we calculate it the other way here, then the versus here, if I look at that engine efficiency, another way that we can write it here is that we could look at the cold, the heat ejected into the cold reservoir, divided by heat hot. So in this case, we know that hot heat here is then going to be the heat from 2 to 3. And even though I didn't write this guy right here, this is Q cold because that's what's ejected into the system. And then this will be the absolute value of heat Q to 4. So if I look at this, this is another way to calculate the efficiency of the engine. Now, which one should you use? Well, it varies from problem to problem. But if I look at this, I could see on the doing it with the work over Q hot, this has more calculations. Why does it have? Because you need 2 works and heating. And in this guy here, you only have 2 terms that you got to calculate. So this has less calculations. So I would use the one on the right here. Now, what I want to talk about next is that I want to look at the diesel engine. So the diesel engine cycle. So I guess what we really should talk about, what is a diesel engine? Well, it's very, very similar to a gasoline engine. They both use internal combustion engines. But I would say here, so I would say that they're both internal combustion engines. But diesel engines have a compression, maybe I should write this big, a compression ignition or ignited fuel, right? Ignition? No, I'm going to say ignited. Ignited injection system, whereas a gasoline engine has a spark plug, a spark ignited system. So if I was to then just say verbally what's really the difference between them, the gasoline engine, as we just saw, the gasoline engine takes a mixture of gas and air, compresses it, and then ignites the mixture with a spark. That's not true for the diesel. So in this case, a diesel, oh, I spelled that wrong. right? A diesel engine takes air, compresses it, just the similar style of the gasoline engine, and then injects fuel into the compressed air. Now, this is important here because the heat of the, let me be careful. I was saying heat. Let me say that. The compressed air is now at a high temperature. Remember, no heating is done here. It's the compression that causes the increased internal energy and therefore temperature. So the compressed air is now at a high temperature, and the fuel spontaneously ignites. Now, what I want to do here is that I want you to remember when we looked at adiabatic compression. So remember the fire piston, and when we did the fire piston with the video, that was an adiabatic compression that ignited a small piece of paper in the piston. So the same thing happens. The same thing happens. So in this case, the compression not heats up the air, increases the temperature of the air quite a bit. And so you're not heating up the air. God, I keep saying heat. You're increasing the temperature. You're not heating up the air. Now, another thing that's really interesting here is that we should talk about the flammability between gasoline versus diesel. So what I'm going to say here, I'm going to show you a video right now. So if you toss a lit match into a puddle of gasoline, it ignites immediately. In fact, it gets hot very, very, very fast. But if you do the same thing to a puddle of diesel fuel, you're going to find out that it's much less flammable than gasoline. So in order to make it flammable, you need an intense pressure to ignite the flame of a diesel engine here. So let me go share my screen here. Okay, let me get ready. And so again, this is a short video, and it's right here. Okay, let's make sure that I got the right share. I do. So now, here I go. Check this video out. So I'm only going to run this for about a minute and a half. Okay. Okay, so the thing that was really important here, as we start to look at this thing, note that they were talking about the flash point. That's the point that where it actually ignites. For gasoline, it's negative 23 degrees C. For diesel, it's 55 degrees C. That is a big, big difference right there. Okay, I thought that was a good video. So now let me go back and start talking about the diesel here. So now if I look at a diesel cycle, it's very, very, very similar. But what does the cycle look like? Here we go. So what we're going to, you know what? I think it might be best to go and look at this idealized diesel here. So now what I'm going to focus on is that I'm going to look at a diesel cycle. And what you want to pay attention to the diesel cycle is that it's going to look something like this. So again, here's my P and my V. And when you look at this, let's just go through the cycle before we go in and look at the next video here. So I'm going to start right here. This is going to be my state one. And again, this is that V max, right? So the maximum volume is again given by this ratio value that we were talking about. So now what actually happens? In this cycle, it's different here because now I have an adiabatic compression. That's not what's different. They both start with an adiabatic compression. So if I go from 1 to 2, I'm seeing here is that from 1 to 2, I'm going to have an adiabatic compression. Now, if you read the language, everybody will say, oh, there's heating going on. There's no heating going on. It's an adiabatic compression. So what I'm seeing here is that adiabatic compression immediately tells us that this guy is zero. It has nothing to do with heating, even though they say that. So what happens here is that this is a compression, so it increases the internal energy of the gas. So as a consequence, what you're seeing here is that there's a huge increase in temperature without heating. When you go online, they keep saying the word heating. That's not possible here. So if I have a volume, now what's going to happen is that now the next step here is that I'm going to go from 2 to 3. And what you're seeing here is that here's what happens here. So what happens here is that right before I go from 2 to 3, note that this will then be isobaric expansion. And if I say isobaric expansion, then that means that the heating from 2 to 3 plus the work from 2 to 3 must then change the internal energy from 2 to 3. So in this case, this is a positive quantity. The internal energy has to increase. So now Q hot, in this case, is Q23. So this is a quantity that we're going to have to compute right here. So then here's where the key point here is right here, right before it gets to 3, there's you spray in the fuel. So now as you spray in the fuel, you get fuel ignition, which then that's the big difference. There's no spark plug. It's this high pressure that becomes super important, right? I would say this is the significant difference between the two. And so now we get to the power stroke. So the power stroke, as I go from 3 to 4, this is the so-called adiabatic expansion, which is the power stroke. So when I look at this thing, we could then see here, again, there is no heating because it's adiabatic. So then, because I have an expansion, that has to reduce its temperature. So now the gas particles are losing microkinetic energy as they collide with the piston head here. So now, once again, there's now a decrease in temperature. And then finally, I got to get back to my initial state. I then come, you know what? I did not do this. And again, this is an adiabatic expansion. This is an adiabatic compression. Oops. And then I finally have an isochoric cleaning to get back to my original state. So here we could then see that Q cold, this is what's ejected, is then going to be the heat from 4 to 1. But because this is isochoric, that's got to be 0. And therefore, the internal energy from 4 to 1, this is negative. So we now have a decrease in temperature again. So if I look at my cycle here, again, calculating efficiencies, there's 2 ways to do that. There's the efficiency of the engine where I can look at the work over Q hot. So in this case, it's got to be the work of 2-3 minus the work of 1-2. That's the only work that's done in those cycles here, divided by Q hot. So then if I look at this guy is going to be my efficiency. The last one that we can look at is that we can now compare this to 1 minus Q cold divided by Q hot. So in this case, this is going to be 1 minus Q cold. So this is the absolute value of, or 1 divided by the absolute value of, what is it, 2-3? Yes, 2-3. So which one's better? You know, that's a hard one to say. That's a hard one to say. both of them require three things to calculate. And the reason why you need three things to calculate, actually, again, this one requires two calculations. It might be that the ratio of the heating is faster because you got isobaric heating, so you could use, NCP delta T, whereas the isochoric cooling, that's just going to be NCV delta T, which, you have to look to see which one's best.